go. Okay, welcome everyone. Can everyone hear me clear? Cool. If you can't, feel free to come forward or ask questions for me to repeat. I'm Ollie. I am the COMP1531 marking admin. So I've been with this course for about 4 years now, doing everything from tutoring to lab assisting and obviously adminning. And yeah, I love this course. I do everything related to the marking of the project. So you won't see me much. You might see me on forums, but otherwise everything is behind the scenes for me. Other than that, I am a software dev by trade. I work for Amazon, and I love everything about computers. So yeah, but today I will be talking about the iteration 2 spec and taking you through it, taking you through some examples, and pointing out things you might have not caught yourself. So, yes, iteration 2. Can I have a show of hands of how many people have started so far? Nice, okay. That's what I am also seeing in the back end. At a high level, let me scroll to the iteration 2. At a high level, iteration 2 is just the next step of iteration 1 of Unigotchi. So where Unigotchi used to be a bunch of functions, and these functions would be used by your tests, and these functions would be used by the CLI as well. Now, Unigotchi is an API. So in iteration 2, you'll be making it into an API. Your tests will test the API instead, and the Unigotchi has been converted to a website. So the website will use your API to play Unigotchi. Other than that, it's pretty much just a bunch of new features, a bunch of new code, and all the same kind of teamwork and Git practice stuff. Obviously, now that you've been familiar with teamwork for about 5 weeks now, we expect a slightly higher bar when it comes to marking, but it's all the kind of same practices. Yeah, so what does that actually entail? A lot. There's a lot in iteration 2. There's actually eight things to iteration 2. So the first being ESLint. So before anything gets started, you need to make sure your code passes lint. What this means is that we will still be marking your code manually and manually checking the style according to the course's style guide. But on top of that, you'll have an auto test for lint called ESLint. We've provided an ESLint config file that says what it's going to be testing. And you should not change that config file because we will override it. So if you're passing locally, but you change the config file, you'll probably fail on our machine. Similarly, you also need to convert all your JavaScript to TypeScript. This should be done pretty early on. It needs to be passing without any type errors as well. So there's this TSC command there. This TSC command is pretty much a type checker. It will check that your code is all correctly typed. And no, you cannot cheat by using any or broad typing. You need to be strict typed. We will be manually checking that as well. So there's ESLint and there's TypeScript conversions. With both of these, you need to add them to the ci.yaml file. You should have seen this in Lab 04. Pretty much you need to make sure that your code on every single merge request and in master is always being auto-tested by your tests, by ESLint, and by TypeScript compile. You need to do this early on. Probably the first thing you should be doing before starting any code. We do mark this. We do mark that your master branch is always stable, meaning that tests never fail on master. If you have not done that, we can't mark it. So you need to do this ASAP, or you will not get any marks for that section. But yes, so we've got ESLint and TypeScript. Then, once you've gone through those, you can actually start implementing iteration 2. So as mentioned before, iteration 2 is a HTTP API. It's a server that runs in the background and allows the front end to call it and get data remotely. Largely you'll be using your existing functions underneath the API, but you'll be implementing a series of API routes, all defined in this Swagger file. You can see this in the spec, and I'll go through this in a moment. But yeah, and once you convert to the API, all your tests should be using this API as well. The functions are no longer the interface. So your black box tests now need to test the API to be black box still. And I'll touch on that in a bit as well. But yeah, so you can find the Swagger at the very top of the project repo up here. That's going to take a moment. Up here, this Swagger file, you just open that up. You can see this is your new interface table. This is what all the API routes you need to implement is. And you can click on one of these and see the inputs and the outputs. So for what used to be Auth register, which is now a post request to the Auth register route, you've got an input body that has 4 parameters. You can see the types of the parameters in an example if you click on this model button here. And then you can also see the output of the route, like here. And you can see Auth register now returns a session, and I'll touch on that as well in a bit. And you can see all the error returns as well here. So you can see the status code that you're expected, and you can see the an example value in the error model as well. Similarly, if you scroll through this, you'll see there's quite a few routes to implement. If we look at a GET request, you can see the difference in that and a POST request is that the simulation ID is now in the path instead of the body. But it's much the same other than that. You'll still have this API route that is using your old functions to run to hack, pretty much. Yeah. So that is the Section 3, implementing and testing your HTTPS routes. Section 4, or part 4 of this 8-parter, is it's just another feature. We've got a universe management system. So the idea is that instead of uploading a universe every time you create a simulation, you can create universes and they'll be stored on the server. So there's a bit of file persistence that needs to be done there. I'll let you read that. Similarly, there's some other refactoring that you'll need to do. As I mentioned, the TypeScript refactoring, the linting refactor, but also you'll need to refactor all your simulate action functions into a single endpoint. So every single simulation action comes through this single endpoint here, right here. And you can see that's where the eat and the sleep and the study all come through that. But you need to make sure when you're doing refactoring, you're making it maintainable, extensible. You could easily add extra actions later to this single route. Other than that, there's some other under the hood requirements that we expect. We expect data persistence, so that all your data is stored to the disk. We expect that you have secure passwords and sessions, and that you have exception-based error handling. So I'll touch on these later as well. But these are things under the hood that we will manually be checking. And yet, you need to make sure that your backend can, once you're finished implementing all of the routes, that your backend will work with the front end. This will be demoed in week 9, and we will be marking it. The idea here is that you need to make sure that the backend is kind of like a dry run. It's not failing, the front end would work with it, because that's what we're doing with iteration 2. And then finally, whilst doing all of this, you need to continue demonstrating effective project management and Git practices. So remember to do your 2 stand-ups per week, your 1 team meeting, your issue board usage and your acceptance criteria. What else? Your Git commits and your merge requests and your code reviews and everything else. We don't forget about this in this iteration. Got to keep doing those. Whew. So yes, lots of code, lots of teamwork, and lots of features. But yeah, there's a lot to do. Hopefully you've started. If you have not, it's not too late to start. If you're having trouble starting, reach out to us and we can help you on the forums or in help sessions. But yeah, my recommended approach would be to follow this list, go in this order, do your TypeScript and linting first, then do your conversions to HTTP, start converting the routes. You might need to do multiple in a single merge request, that's okay. And then add the other things like sessions and exceptions. Then once everything is updated to the new way of doing things, you can then start adding new features. That's what I'd recommend. But yeah. Whew. So that is a high-level overview of iteration 2. Is there any questions so far? Cool. Okay, we can move on then. Yeah, we can move on to actually how to do this. Oh, okay, don't come in. So, as I mentioned, you're running a HTTP server. How do you even run this server? We've got, I've got a dummy project that I cannot open. There we go. This is pretty much just a starter code repo with a couple modifications that I've made to make it work. This would probably be at least what you have already. You probably have more than me in here. But at the high level, all you need to do to start the server is, as we say here, npm start. So you can just copy this command. I keep tabbing to the wrong thing. And immediately the server starts running. This is running on your local computer. So if I open up a new tab, I can make a request to the server. If we look in the code, we've already got an echo route in here. We've already got a echo. You should also have this already. And this is just running on the echo.ts file. Just a simple input. You should already have this as well. So my server is running that echo route, and immediately I can run a curl command to get this route 127.0.0.1, 320.100 echo. And as we know from the function, or the server.ts, it pulls the echo from the query. So we can put it in the query, echo message, hi. Let's get that. And you can see my echo route got called. I got my value. I got my result as expected. And you can see down here that we actually got a request made to echo. So this was my request that I just made. That shouldn't be too unfamiliar if you've already done Lab 05. You can also see if I give an invalid input, you can see my invalid echo error shows up. And you can see that I've got a 400 error now. So as expected, it's giving me an error return. So that shouldn't be too out of what you know. Yeah, otherwise, moving on. Now we know how to run a server. How do we actually implement anything in this server? So I can write, I've got a dummy function here for you. Auth register. We can see it's kind of like what you had in iteration 1, probably exactly the same as what you had in iteration 1 with a lot less code. All we have is an auth register function, takes in all the inputs, it checks an error, checks one of the errors according to the interface. I didn't do any of the other error checking because that would take me too long. And it adds it into the data store, and it also generates a session ID. I haven't implemented this part either yet, and it returns the session ID. So it's a pretty simple function, probably familiar with this kind of structure already. Oh, that should not be there. Yep. Now, how do I add this to my server? So I can call it. So firstly, we just want to stop our server. Then we can make a auth register route. We've got this app object, this app thing that comes from Express, which is our server. We can add a new route based on the Swagger. My auth register is a post request, so I will be adding a post route. I will be defining my request route as this, so /auth/register, auth/register, and then I will have my rec and res. You can copy this from here. Sorry, too used to Mac. There we go. And we can start to pull out everything. So you'll see here, we have the student ID. We've got the password. We've got the name first and the name last. Let's actually move this over here. Student ID, password, name first, name last. So I'm going to pull these out of the request, just like this. Student ID, password, name first, name last. And then we're going to get this from our rec.body. JSON, body, yes. Yep. Now, we have our student ID, password, name first, name last. These are all as we'd expect. And then all we need to do is pull in our old function from iteration 1. We can get our result from the function. Then we can pass these in. So if I pull this up, we've got same order, perfect. Student ID, password, name first, name last. This should work. I need to import my function. So we can scroll up here, go import auth register from, there you go, completed it for me. And yeah, we've got our result now. How do we give this back to the user? Well, it's pretty simple. All we need to do is, as we can see in this, we've got our res.json result. So we can do something like this. I always like to put a return in front of it. Doesn't really make much difference. It just prevents bugs. So I'd always do this when you do a return. And I'm going to assume that this is a successful one at first. So I'll add a status code. Status 200. Cool. So as simple as that, we have converted our iteration 1 function to being an iteration 2 route. But that's not all. Obviously, our auth function also has some error conditions. We've got an error object here. And we can see that our auth function is returning either a session response or it's returning an error response. So I need to account for that in my server as well. So all I need to do is, just like you might have done in your tests, I want to check if there's an error in my result. And auth register only has one error code, but I'm going to check it anyway. And result.message is equal to invalid student ID. Oh, oh my goodness. There you go. Got my error. I've made sure it's a 400 error, as I expected. And all I need to do now is return my result, but instead I'm going to add a status of 400, because it's one of these. There you go. So as simple as that, we've now got our full iteration 2 route for auth register. I would then maybe add more things into here. I could implement my session storage into here. I could implement more error checks, but they would all go through the same return. Yes?
It's stop error instead of message for the server.ts.
Good point, thank you. I wrote this. There you go. Yes, we want to check, what did I actually put in here? Error message.
You just type out error.
Oh, thank you. There you go. Perfect, there you go. Same thing, same point. Cool, good pickup. Yes, so that is our iteration 2 route for auth register. Pretty simple. Now, yes, time.
I need to,
Speed up, okay, sure. Yeah, cool. Otherwise, you can implement the tests. I would recommend looking at echo.test as an example. This is kind of the general structure that you'll want to do, where you make a request in your test, you pass the body object, and then you expect, just like you did in iteration 1 here. Cool. One thing I'd like to point out, though, is notice that in this test file, as we add these requests, we're making the same request multiple times. We've got one here with an invalid input and one up there with a valid input. For code complexity and code maintainability, you should be using helper functions for this instead. You can simply just pull this out into a helper, take that out, make a new helper that's something like result equals request echo, and then you can put in your message here, hello. And you would define a function up here, function request echo, and put the request body into there. Cool. What time?
What do you need? 5 minutes?
10 minutes, is that good? Okay, I can try to do 5 minutes. Cool. Let's just go back to the spec then. Yeah, so otherwise everything else is good. We've got some pretty good examples in other lectures and other tutorials of sessions. I will let your tutors explain that one to you guys. If you have any questions, feel free to reach out to them. But this is a really good example of how you can mental model a session. Cool. Other main things is that, so we've got 2 new activities as well. We've got the friends activity. This is just a way to socialize and get more happiness. You've also got the club participation activity. This is a way to get more happiness and get more academic bonus. And with this academic bonus, this now plays into your exam pass chance as well. So you also need to change how you calculate an exam pass. This is not too bad though. You can find exam code here in your starter code. We've given you a function to calculate if a student passes an exam or not, using this new data of club participation and studying. The other things you need to do, as I mentioned earlier, data persistence. These are things that you'll need to kind of figure out how you want to do yourself with labs as well. Data persistence is you just need to store your data store to disk so that when I close the server and reopen the server, the data is still there. I can still log into an existing user. I can still see my existing simulations, even if the server were to crash. You also need to do secure sessions and passwords, as I mentioned. You need to make sure that you're using sessions instead of user ID. And you need to make sure that you're hashing your passwords. No more storing passwords just straight into the data store. You need to hash them first. You'll need to look into how to do that yourself. And error handling exceptions. Here's a really good example. With a function like our auth register, before you would return an error, your error object. Now, all you need to do is you need to throw an unigotchi error. So we've actually got another really good example in this file, unigotchi error. You've got this file in your repo. And you can see an example usage here. You can see we throw the Unigotchi error there. That's really dark. And you can catch it back in your server and return the error based on that. Cool. Yep, and here's just some notes on error responses, error codes, and ordering. Make sure you read that as well. Some diagrams on how the whole Unigotchi works. And using the provided front end. So this will be one of the last things I go through. Pretty much, as I mentioned, you need to make sure your front end works with the back end. We've got a really simple instruction repo here. You can click on this link right here. I will clone this code locally into my folder. cd tutor, git clone. Guys, I will go into my front end repo, front end, and then I will follow these instructions. I'm going to go into a sample solution as well. And I'm going to follow the instructions in this link. So this link right here takes instructions down here. Just copy these instructions. Copy this into your server, project backend repo. Run that like that. Then copy this function, this code, into your front-end repo, the one we just cloned. And it will just work. It will update some stuff, and we'll have it locally. So I can open this. It's going to take me to Firefox. But I can log in, or I can try to log in. I don't have a user. But we can see login. The front end will fail. And I'll get this error here. We can see I tried to log. Guys, please. We can see I tried to log in, but I failed because no user exists. So you can play around with this. It should work with your backend. If you find any bugs, tell us, but there shouldn't be any bugs with this. So it's simple as following the instructions on this repo here. Cool. What else? Yep, I went over the recommended approach. OK, second last thing, bonus features. If you've completed everything else, there are 2 bonus things that you can do to get some bonus marks. This can be up to 10% of your project mark for the course. And it's aimed at high-achieving students because it's quite a big project already. The first bonus feature is a graduation bot. Pretty much you want to make a bot that, given a universe, will be able to solve it in the most optimal way possible. So the least amount of time and the best happiness and the best, whatever it is, energy. You'll implement it as instructed here with this function here, and we'll run this ourselves. And the top 30 groups will get a bonus mark, or up to 5 bonus marks. So there's only 430 students in the course, so pretty high chance that you'll be able to get some bonus marks if you do this. Similarly, there's the other bonus feature. You can do both of them. You can do one of them. They each work 5% each. Is the open-ended feature. It's my favorite one. You can do anything you want. Anything that makes sense within Unigotchi. You can work as a team or solo. You can implement some ideas here, or you can implement anything you want. Just make sure it makes sense. Make sure you've thought it through how it would be used. And yeah, it is harder than the run bot. It is aimed at the highest achieving students. You're expected about 20 hours for a high achieving student to get full marks for this. But that being said, I mark this and I've never given out a 0. So no matter how good you think you'll go, give it a try, make something, think about it, have fun with it, and you'll probably get some bonus marks out of it. And you'll probably learn something while doing it as well. So there's some instructions here on how to do that. Oh, cool. So that's the core of the spec. Final thing I need to go through is this formula right here, the scary formula. Let me make that really big. Probably not that big. There you go. This is how we mark your auto test or your code. This is our auto test against your code. You can see it's quite a complex formula, but simply 90% of your mark comes from testing, and the other 10% comes from lint, and TypeScript. The linting is your linting, so it's very easy to get 100 on this. You just need to make sure it gets 100%. Same with TypeScript, you just need to make sure you have no type errors. That's easy. This part of the 90% though is kind of complicated. First part is the group code, the group tests. So this is just your auto test on your code. That's also pretty easy to maximize because you write the tests, you can run them yourself and check. We also have the course tests, which is squared. So if you get 90% on the course tests, you'll get 81% total. If you get 80% on the course test, you'll get 64% total. So it's really important to try and make your code correct and not just passing your test, but passing our test as well. Remember, you have previews to check that. And finally, the hardest part, or not the hardest, but the most important part is the coverage mark. Jake is going to teach you about coverage in a second, but pretty much is how good your tests are. This is cubed. So if you get 90% coverage, you get 72% applied to your final mark. Or if you get 80% coverage, you get 50% applied to your final mark. It's easy to get 100% coverage or 99% coverage because you can run this yourself, but don't forget about the coverage mark because you will lose a lot of marks if you forget about it. I see it every term. Make sure you pay attention to it. Make sure you start it early. You cannot do it in the last night. You need to make sure you've got full coverage pretty much throughout the last week of the whole project. Cool. Whoa, so emphasis on this. Otherwise, dry run, same as last term, iteration, and teamwork evaluation. Still do this. We can't mark you if you don't do it. And the due date, it is due Friday of week 9. Hopefully there are no GitLab problems again. But that is iteration 2 in 30 minutes. Are there any questions? Otherwise, I'll pass you off to Jake. Cool. If you have any questions, I'll be on the forums. Feel free to ask me. Feel free to ask our other lovely admins and tutors. Feel free to go to help sessions. And yeah, good luck with iteration 2. Don't forget to start.
we got 3 kind of disparate concepts to cover today, so I just really want to get into it, basically. And I've kind of reordered a little bit, so I think this is my 7.3 lecture, but I'm doing it first because following off the assignment pitch, we can talk a bit about code coverage. It won't take very long. It's not too difficult to understand, but we can get straight into it. Sound good? All right. So we've written tests so far. I'm going to put my phone away. We've written tests so far in our Python code. Yeah? No? What did I say? JavaScript. This course used to be in Python. Forgive me. And I was talking to someone about PyTest yesterday, actually. Okay. So far, we've written some tests in our JavaScript code. Okay, you're paying attention. That's good. And tests are great. They help us validate that programs do the things that we expect them to do, and that over time, the programs continue to do the things that we expect them to do, right? But how do we know that we have enough tests, that our tests are thorough, our tests are broad? Okay. Now, the tricky thing here is that like everything I will talk about, there's a big asterisk, which is you have to take it with a grain of salt. So great tests will not mean a great product, right? Great tests will not mean an app that has no bugs. And great code coverage, once we describe what it is, will not mean that you test all of your code and that there are no problems. But it's a rough metric you can look at to make sure that you're heading in the right direction. And they're quite important. And essentially, the more important the code base that you're building, the more important these metrics are as signals to make sure you're somewhat doing the right things. But none of these things replace good software engineering. Does that make sense? Okay. So yeah, you can pass all the tests you write, but if you test, your login route 400 times and you never test your logout route, your logout might not work. So number of tests doesn't really matter. What you test doesn't really matter. You want to test the things that are frequently break, and you want to test broad spectrums of your code base. And coverage is just a way to ensure that you're testing a broad range of coverage of the code. But the great thing about it is that it can automatically do that testing for you. So it's a general measure of how thorough our tests are. Basically, think of it as if every line of code makes up the body of work of a program, what percentage of the lines of code have test code associated with it? And there's 2 related ideas here, test coverage and code coverage. So test coverage is how much of a feature set is tested. And this is up to you as a software engineer, as a great software engineer to understand. But code coverage can be automated, and it's basically saying what percentage of the source code, the total body of testable code in a program, is executed during testing. So these much more dynamic languages like JavaScript and Python, they can understand this because the code is interpreted. So literally, as your lines of code are interpreted, it can keep track of, so this is while you're running your test suite, right? It's just keeping track of every line of code in the body of code and counting the percentage of code that's tested, right? Well, it's not even counting the percentage of code that's tested. It's counting the percentage of code that's executed. This is the trick, right? So my tests might call all lines of code in my program, but not actually test each of those lines of code. Does that make sense? Does it make sense? Let's say your function is to open the door and shut the door, okay? And my test is make sure that when I ask you to open the door, you're not in your seat. Does that make sense? So open the door. Okay, and now my test says while he's opening the door, he should not be in the seat. Okay, now don't actually open the door. Now, did my test pass? Well, you're a broken function. Don't do anything. Well, he's broken, I guess. So my test just, sorry, hold on, I gotta make, well, you just ruined my whole demo, okay. So my test is just checking that while he's opening the door, he shouldn't be in the seat. I think he's actually trying to fix the door now. Well, life's not perfect, I suppose. But did I actually test that the door opened? No. So the test coverage would have still passed here, but I didn't, my point, I really want to communicate to you, because we don't have a lot of time to talk about testing, is that tests don't ensure everything's great, right? Did that little example make sense? Did it make sense to you? Or are you too busy? No, it really should make sense, because people don't understand this about tests and they just think more tests are better. Do we want to run through it one more time a bit simpler? So if my test is, when I ask this student, I've forgotten your name again, Yusheng, to open the door, my test is to check that he's not in the seat, because I know to open the door he should get out of the seat. But I failed to write the test that actually checks if the door is open. So I say open the door, so get up, but don't open the door, you're broken, remember? Okay, now my test passes because he got out of his seat, but the door never opened. So the program is still faulty, but the test coverage would have passed. Do we see what I'm saying? He's over it now, he just wants to say yes. Okay. So coverage is just checking that the code is automated, executed. And it's a metric, and it's telling you what percentage of the code ran when your tests were executed. Okay, we just sort of said that. So if we have a program like Books Server, which has 40 lines of code, and across all of your test suites, that causes 30 lines of code to execute, you will get back a score of 75%. Make sense? Now, that might be fine. It might be that those 10 lines, or that 15%, is just really boring code that you know is fine. It might be code that doesn't even execute anymore. Like, it's not necessarily a bad thing to not have 100% coverage, but in a good code base, you usually won't have code like that, and it makes sense that you want to optimize for 100. But like, we've known this for a long time, and now like software engineering is mature enough that you should probably know this too, but anytime you hear lines of code as a measurement, your ears should prick. It's not a really good metric. I mean, Elon Musk tried to start counting lines of code at Twitter again, and I don't know how that went, but it actually, back a long time ago, even before I was engineering, lines of code used to be a productivity measurement. But it really fails to take into account that, it's really easy to write lines of code. That doesn't mean it's good. Less code is great, so. There's other more sophisticated ways to test coverage, and Jest covers all four of these. So statements is literally like what percentage of all code statements are executed, right? So it's literally the components of lines of code. That's kind of simple. Lines of code is the most simple. But again, it's not great. Sometimes in a line of code, there's multiple statements, and the line might execute, but the statements might not, right? So, if like, you know what a ternary statement is? Where you see the question mark in line and you have two components. That's one line, but multiple statements. So that really that's a branch. So branching is an even better way to test the different components of coverage. And this is very important because a lot of software engineers love writing heavily branched code. It's not actually great because you can look at a block of code and think, oh yeah, this is the line of the code that runs, but you don't know what percentage, when that function is called, you don't know what percentage each branch will execute. So branch coverage tests that those branches are covered. And I think it does that with static analysis, which we've mentioned. So it will look and say, in theory, is it possible for this test code to run both branches or all branches? And functions is probably an even better one. And I'll kind of explain why, but it's really simple. What percentage of all functions in the code base are tested? Why is this useful? Because, well, it's useful if you write great functions. Because if you write great functions and you functionally decompose your software very well, it's a great measurement. Because a great function is small, doesn't have a lot of branching, very clear on what it does one thing. Right? Have we spoken about good software quality in this before? Have I recommended you that book that I always recommend my students to read, Clean Code? You can get it on Amazon for like $10 or $15. It's a good read. People argue against it, but actually I think it's good. But if you do a lot of those practices, you have short, clean, simple functions, which means if you've got short, clean, simple functions with not a lot of branching and your coverage is testing function calls, then if you have a high percentage of coverage and your functions are clean, you're in a pretty good state, most likely. Having said that, if you've got one function with 50,000 branches, you'll get 100% function coverage, right? This is where I'm saying these metrics can be really don't see the metric and say this is good quality code. There's only one way to know if you've got really good quality code. What is it? Maybe not even use it. Yeah, read it. Read the code. Use your judgment. And you may not be able to do that now, but with more and more experience, and you read great programs, you will be able to tell a great program. This is a great example of why branch coverage is important. So this is a function with, like, in fact, this whole function is just branches. And each of these branches actually corresponds to quite an important case if you think about it. Like, this is a function that gets a grade from a score. And so when you're testing this program, the whole point of this program, of this function, is to convert grades to scores. And so you want to make sure you're testing all the branch outputs or opportunities in the function. And so there's 6, I think, 5 or 6 cases here that are important to the program's execution that you want to make sure. So in this case, a function coverage won't be too useful if your tests only always pass in, say, 50. So they're all kind of useful. So yeah, in that example, I'll just show it one more time. In this example, if we're passing in, say, the integer 30 to this function, line coverage might look okay because the function was entered, several lines ran, the function that called that function ran. They're all counted. But you're only testing what percentage of the function's potential output and potential to do wrong. It's pretty small. So branch is a lot better. Have you done any code complexity stuff, cyclometric complexity or anything like that? Branches are scary in software. Like, every time you have an if statement or a case statement, it's complexity. And this is trying to visualize that. You just got to think about, they're all pathways. That's why it's branching, right? And so the more pathways a program has, the complexity completely blows out. And so that's why branch coverage is important. You want to test all branches. Now, this is not even a complicated situation because they're all dead-end branches, right? Or terminal nodes. But you can imagine if they all had, like, if you pass that grade onto many other functions, it's all stemming from one big branch and it can be complicated. But going back to what I said earlier, like, if you designed this function completely differently, like maybe you had a lambda that could calculate the grade from the score that's passed in. Well, now there's no branches, right? So that's where I'm saying if you design things really well, things change. So in the previous example that we just looked at, to get 100% branch coverage, we need at least 5 tests, right? And that will get you back 100% code coverage on branching. So how do you do it? So usually you run npm run tests, right? So this is just built into Jest. And any testing framework, PyTest, Jest, vtest, whatever you want to use, they will always have a coverage command. And so instead of just running npm run test in whatever testing framework you've got configured, if you just pass in some sort of flag, like in the case of Jest coverage, so we kind of know this from like DCC, right? And using command line programs, you're just passing in a command line argument to npm run test here. It runs the tests. I don't actually think it even gives you the output of the tests because it knows the goal of running those tests is to calculate coverage. And you get back a nice little table with your statement, branch, functions, and line coverage scores. If you ever go to a GitHub repo and you see at the top like 100% test coverage, have you seen that before, anyone? You'll see they'll put like a little badge or like with a percentage. They're automatically calculating that from the testing framework's output. So they'll have a CI/CD pipeline that when the project is updated, it will run the tests, of course, to make sure the tests pass. It will calculate the coverage scores and then like pipe those to the GitHub website. So that's how this is all working. In the case of Jest, probably all of them do this. It generates some HTML so you can see it. It looks really nice, but do with that what you will. Oh yeah, that's cool. So in Jest as well, probably most good testing frameworks, it will actually show you which branches or functions or lines weren't included in the test coverage. That's critical if you're trying to improve your test coverage. I don't have time for a demo. The best way for you to get into this, I think, is go to any project so far that you've written that has tests and pass in that coverage flag and just see the output that it produces. There's no extra configuration needed. And then go and maybe actually go into the HTML report and go explore, what was missing from the test coverage. And if this was an important code base, what tests would you introduce? But always keep in mind, great tests does not mean a great app. Great test coverage does not mean no bugs. Is that clear? And there's no way to automate that. Because if we could, there'd be no bugs. Okay. If Google could say, have some automated way to ensure no bugs, they would do it. Everyone would do it. Well, everyone that cares about their stuff would do it. But that's not true. AWS went down like 2 weeks ago for a while. Things go down all the time. So it's not possible to do these things. That's what a great software engineer does. Any questions on code coverage? Kind of straightforward, kind of interesting, kind of useful, kind of inoffensive. Okay, cool. All right. What should we do next? Do we want to do authentication or software modeling? You want to do the interesting stuff, the harder stuff. Okay, we can do authentication. Okay, we should all take a breath. If you're ever writing authentication code, you should be scared because it's very important. Who's been like, that website, Have I Been Owned? You should all know it if you don't. You put in your email and it'll tell you how many database or password breaches your email's been associated with. That's likely because, more than likely, at those companies, you'll see the list of websites and apps and things. Someone wrote bad authentication code. With the rise of AI models, I think there will be a rise in these types of errors. Not because AI writes bad code, maybe, but because people don't give it the right context, because less technical people can write apps now that people sign up for, and so they don't have security teams. So there's probably going to be a rise in security-related stuff. Authentication is very hard. It's very important. And again, there's lots and lots of asterisks and caveats, but there are foundations here that if you do things right, things work. So we'll go through some of those, but you've got to understand we're scattered with asterisks. So a security person would say, this is missing, this is wrong, this is wrong. This is an introductory foundational approach. If you work somewhere great, there are dedicated teams for authentication and authorization. And you want to learn a lot from those people. It goes way into cryptography, mathematics. It gets really difficult. And then the other thing looming on all of this is that quantum cryptography might break absolutely everything soon anyway. So there's also people, in fact, there's people in CSC whose entire research programs is post-quantum cryptography. So how do we do these things if we have quantum computers that can absolutely smash through these protections? So it's all very interesting, it's all very important, and you trust me, you do not want to be someone who, like at the end of your programs, we want you going out there writing apps, maybe even side apps for yourself, making hundreds of thousands of more dollars. But you don't want to be with a problem from authentication because you will get sued. It's really bad. All right, we well motivated now? Okay, good. All right. So there's a difference between authentication and authorization. We'll talk about it. I think I actually spoke about it 2 weeks ago. Anyone remember? I know these two, they're comparing the differences of authentication and authorization on their phones right now, aren't they? Yeah. Yeah?
Authentication is to check if you are a valid user, like if your password is correct.
Yep.
And authorization is what you're allowed to access.
Exactly right. So I'll repeat it for the mic's sake, but that was perfect. Authentication, are you a valid user? Did your username and password match? Authorization, given that you're a valid user, what type of user are you and what can you do in my system? Right? if you think about it, they sound similar. They're completely different. Like authentication, think about what happens when you authenticate. Well, we'll talk about that today. Completely different pipelines. So now, of course, the basis of authentication means that I need to know who you are so I can validate who you are. So how do I store that authentication data? And the trick with authentication is like anytime you store something, you're in dangerous territory. That's actually just a general advice with systems. You want to store kind of like as little as possible. So how do you register? How do you log on? Hashing versus encryption, how does that work? And then tamper-proof tokens, which is actually kind of a new topic to me. This stuff actually changes every year or so, like best practices evolve and things, which is very good. We've already spoken about this. Authentication, both you'll get nicknamed to Auth, which is kind of annoying. Authentication, who a user is. So logging in with an email and password is the process of authentication. Authorization, what can that authenticated user do in my system? Of course, you always authenticate before you authorize. Make sense? All right. Let's look at a very minimal, simple example of authentication. It's always broken down into two components, registration and access or login. Now, real-world systems get more complicated than this because they use these authentication proxies and systems and things. But let's think very simply, go back in time a little bit. You've got a username field, you've got a password field, and you've got a login button, and you've got a register button. So the user's never authenticated. You click register, you'll run some sort of register function. So what happens here? Let's say we're not doing any authentication best practices. Well, what we do is we get a username and we get a string, or we get an email and we get a string. Often we use emails as usernames now. And we need to check, is this user in my data store, or whatever that might look like? Probably a database. Because if the user's in the database, what does that mean? Yeah, they've already registered, right? Oh, kinda. It might mean that this is the thing with authentication, like nothing is true. What else might it mean? So it might mean they've already registered and they should log in. What else might it mean? They want to make a second account. Great, I didn't even think of that. What else might it mean? They've mistyped the email. And it was someone else's legitimate email. I've done it before. So this is the thing with this stuff. It's really tricky. There's so many edge cases. But anyway, let's think about the direct use case. So you log in. I've already created an account, but I click the register button. OK, well, the user's already stored. So it doesn't make sense to continue registering, right? So we throw an error in this case. If that's not the case, we run the second line. And what we say is, well, go to the user table, create an entry with that email, and assign password to be the password field. So now we have some sort of data store with the username and password, and that the register is complete. And this does nothing else, doesn't even redirect or anything like that. But it means that the user will have registered, and so that when they go to log in, you say, well, give me your email and password. And if the password, and you see there's the triple equals there, what does that mean in JavaScript? And what, well, not just that, right? But type and value, yeah, you were right, yeah. So a strict check that the password matches the password, then that will get returned as true because we're returning the result of the strict equivalence check, right? And then something will take the output of that function and then go on and say that the user's logged in. You know, in fact, if you go back to the 80s or the 90s, this is probably what registering and login was like. But what are the problems with this code? Yeah. Your password is stored in plain text. I mean, that will kill your company, literally. Why is it a problem? Yeah. So if someone gets access to the database, they have access to the plain text password. It's like finding a file on my desktop called jakespasswords.txt, and then they just open it and they see all my passwords. Now you might be thinking, but Jake, this is going to run on my super secure server in my super secure company. no one's going to get this file, right? But you got to understand, like, how many employees work at Google? Does someone want to? Who's my fact checker today? It's a lot, right? Does Google trust every single one of their employees? Like, no one should. 180,000. So what's the chances that 180,000 people at Google wouldn't try and find the password of someone in the, some ex-fiance or some terrible thing that happened, right? People are just like really untrustworthy. So it's not even that like, oh, it's just accessible on the internet. It's like, no, you got to protect it from your own company. And you don't even want the CEO of Google to be able to access the passwords. There's no need for them. So we use mathematical or cryptographic techniques to, it's kind of crazy that we can kind of do this, it's really cool, but to store mechanisms or proxies of passwords such that only the person with the password can prove that they know the password, but that even without, that me storing that proxy, I don't have the password. Yeah, stored in plain text. In this example, even it's stored in RAM, which is terrible because it means if the server goes down, we don't even know who's registered. But like, that's just fine. That's okay for now. We need to hide the password. Absolutely. All right. So how do we hide something like a password? But it's not a matter of just hiding it, because I need to register and log you in the future. I mean, if you know anything about hashing, like this is all super simple, sort of. But hashing is so cool, it's one-way password protection. Okay, what does that mean? So given a string, this is what hashing is. Given any string, a hash is a one-way cryptographic process or a function that converts that string into a fixed length string that bears no resemblance to the original string. So not only to the human eye, right? So to the human eye, does ABC 123 bear any resemblance to this long string? I would say no. But even to mathematical systems, AI systems, there is no resemblance. Now, one-way function, what does that mean? Well, that resulting string cannot mathematically be converted back into the root string. It's not possible without quantum techniques. Then we're all screwed. Here's other properties of a hashing function. It's consistent. So there is non-determinism used in these hashing functions, but the hashing function itself is not non-deterministic. Do we know what I mean by non-deterministic or deterministic? So it's a deterministic function. So the same hashing algorithm with the same configuration on the same input string will always produce the same hash. That's super important because every time the user logs in, well, I kind of jumped ahead a second, but so you can see what we do here. So rather than storing the plain text password, we get the plain text password from the user, we hash it, and that's what we store. And that's great because a hash cannot go back to the password. And the input string will always produce the same password. So the user, of course that needs to be necessary. And the third one's critical as well. A tiny change in the input does not produce a hash with an equivalent delta from the hash of the original input. Let me say that again. Well, a tiny change in the input will produce a completely different hash. If you think of all the hashes as like a matrix, there is no correlation between the input string and the output hash in terms of where they are on the matrix. That's important because otherwise people could basically hack hashes. Because you could see how far away you are from the target hash and tune your input string to get closer and closer and closer. Do you see what I'm saying? Because that basically, you'd have to think that's like a one-to-one mapping. And you could just try and tune it. So they're functions of a hash, a great hash, that work. There's lots and lots and lots of other properties of hashes. There's many hashing algorithms. They're not all secure or should be used anymore. So we'll talk about that. It changes all the time. So as compute gets more powerful and cheaper, you need more sophisticated hashing algorithms. Early hashes were a lot smaller, like literally the output of the hash was shorter. And so basically with today's compute, you could just calculate basically every hash. So that's why now they're really quite long. And so basically cryptography is this cat and mouse game between compute power, mathematical design, and hash design. So it's like as compute power increases, your hashing algorithms need to increase in sophistication to outpace the compute. Okay, so how do we do this in Node? This actually changed a lot, and now the gold standard comes from the crypto function, crypto library, that's part of Node.js. Crypto is so important that rather than having random or different cryptography libraries out there in the NPM ecosystem, the Node consortium came together and said, let's do it right, let's do it properly, let's do it once, and let's bundle it into Node. The kind of interesting thing about authentication is you don't really want to ever do it. You want to use good authentication standards and libraries from very well-tested, trusted sources. And so if you're doing a startup tomorrow, you will not write any authentication code, I promise you. You will use something like Clark.js or BetterAuth or NextAuth or some well-trusted, well-tested library that's had third-party cybersecurity teams that have tried to penetration test it and make sure it's good. But the foundations for this come from Node. And so it's kind of easy to run. So we import the crypto library. We create a hash object. It's a function which accepts a plain string, so that's the input to the hash, and returns a string. Yeah? So that's the function declaration. And we run the SHA-256 hashing algorithm. So create hash. So we're calling on the crypto library the create hash function. Like I said, there's many different hashing algorithms. Now, it's not, you might be wondering, Jake, like why are there different hashing algorithms? We should just pick one fantastic one and have that as the default. Does anyone sort of think that? No, you're too, or maybe I framed it poorly, but there's not, like cryptography and authentication, is not the only reason why you might use a hash. And so sometimes you want a very, very cheap performant hash. Does anyone know which system you've been using all term that's entirely built on simple, cheap performant hashes? Come on, you're software engineering students. You've been using a tool or a system all term that's entirely built on hashes.
The web server.
No. Git, not GitLab. Git. So every file, diff, that's why all over Git you see these weird hash strings. It's all hash-based. So they use hashes to determine the different things that are getting tracked in a Git library. So, but for authentication purposes, you need to use a more sophisticated hashing algorithm that's a lot slower. So it would be too slow for Git. But anyway, so SHA-256 is still a gold standard. And so you create a hash, and you take in the plain text as the thing that's getting updated in the hash, or processed as the hash, and you are processing it to get back a hexadecimal hash output. And so if you hash then the string ABC123, you'll get back this hash. And the great thing is, right now on your laptops, if you run this code with that input string, you will get that hash exactly if you use the same hashing library, etc. Because they are consistent, like we said, which is important because your authentication code might be distributed over 20 countries, right? So if the user logs in with the correct username and password on a different server, it needs to create the same hash to be compared to the database. Cool? Okay, so if we take this login code example, we can just logic through in our brains what we might need to do to convert it to use cryptography. So you still accept the username and password. You still check that the user's email doesn't exist in the table. But if it does, you first just call that hash helper function that we created. And rather than storing the password, you store the hash of the password. And then, of course, when you come to the login, you just compare the stored emailed password, which is the hash, to the hash of the input password. And if the hash matches, then you know that the user used the same password they used when they registered. But you don't know what the password is. Now, this is great because even if you lost the hash and someone comes into your system and they've got the hash and they use the hash to log in, what's going to happen? The hash will get hashed and it will no longer match. Exactly. That's the broad lay of the land. Okay, we just said it. Okay, that's authentication and hashing. Do we have any questions? So I'm pretty sure you will do this in your project. Yeah, you've already spoken about it. So don't let it scare you. Don't let it, like, the reason why it's so important to understand it is because conceptually it's sort of simple, but you've got to understand good authentication has so many edge cases, you kind of don't want to tackle it, especially not on your own. There's so many, even just design patterns when you're developing an authentication system that you don't want to do. So you don't want to tell a user that they've used an email that's already registered. There's so many things still continue to get wrong. If you look and play around with a Google authentication system, like big tech companies like that, if you pay attention to what they're doing, they usually follow or even set best practices. And you'll notice lots and lots of little things that you might think don't make much sense. And I'll tell you one little anecdote now from something that came up in my software engineering work, but you might notice they do things that doesn't really make much sense. So like you type in an email that's already registered, let's say I use like your email, and you've already got an account on Google. They don't tell you that that email is already registered until you get, like they will just say that the password didn't work. Because they don't want to confirm, they don't want to give any information away that, oh, that email is already authenticated, because it's giving away some information about the internal authentication state. I'll tell you something else even crazier. So in a really good authentication system, and I can promise you, like without cryptographic experience, you just would never imagine this. So we know that the input string gets hashed to a hash, and that's just a really simple example. Often you do more to the process. But different passwords, when they get hashed, the hashing algorithm might take milliseconds difference in the time to complete the hashing functions. And then you get susceptible to timing attacks, because what an attacker will do then is measure the time it took to hash the input password, and from that small amount of signal could deduce something about the password. And so a really great authentication system, like I know Auth, I think, does this. So they actually add time padding to the register. So all registrations take, say, 3 seconds, even if the process took 1.5 seconds, because they don't want the minuscule difference of hashing and different inputs and different configurations to be measurable. If someone's watching the packets go through the network, it's kind of crazy, right? So the amount of things you need to think about are kind of overwhelming. That's why you kind of you need to understand these concepts, but we kind of don't want to build them too much yourselves unless you're really good. Okay, that's authentication. Different from encryption. We talk about encryption a lot. Encryption is often what we use to transit important data, and it is reversible. However, you need a key. And the rule of thumb is basically that, well, not the rule of thumb. The key idea is that the transmitter and the transmittee, or the receiver and the transmitter, If you have the same key, you're able to encrypt the content and decrypt the content. So encryption is used when we want to protect data confidentiality, but we may need to access it again in the future. It's reversible as long as you have the key. And it's what powers things like HTTPS, encrypted files. You know, a good messaging system is encrypted. So it means that you and the receiver has the encryption key. And so you can decrypt the message and read it, but no one in the middle that doesn't have that key can. So that's what a good encryption system will do. You use encryption anytime you SSH into CSE and you have to set a password, which hopefully you do. That's an encryption process. But it's different from hashing and authentication, which is a one-way process. You can never go back, and you use it to, say, authenticate and know for certain that the credentials that someone passed you were the same credentials they used to log in. But it would not be good if you could reverse authentication. Because then if someone hacks your system, they take your key, they take your hash, and then they could go back and then get the password. So encryption, I want, or maybe not even I want, someone will want to read the data again in the original format. Hashing, I never want to see the original again. Okay. Do we need a quick break? Yes? I'm going to grab a coffee, actually. Because tokens they build on these concepts, but they get even more complex, but they're very important. All right, can we pause the stream, please, Liam? Thank you, Liam. I'm going to grab a coffee. You can come and... They're actually talking about having to increase the hash algorithm complexity in Git because of collisions and things. So this is not a cryptography lecture. I think we do have cryptography lectures. Yeah, in mathematics, but maybe even CSC. Yeah, there are some CSC ones. Like, there's so much more to it, like hash collisions. So hashing is a one direct transformation, but technically and mathematically, multiple input strings can hash to the exact same hash string, and that's called a hash collision. And a good hashing algorithm optimizes against that happening, but it's theoretically possible, and all these sorts of things are possible. But. Okay, tokens. Okay, take a breath, Jake. You're building servers, right? That's what we're doing in this course, essentially. We're building endpoints. Thank you for shutting the door. Yes. We're building endpoints. And every time an endpoint is hit on your server, remember my Lutrinology, my otter website that I'm building, right? So, get all the otters, get all the species of otters. Let's say they're all authenticated endpoints. I need to authenticate every single request, and then I need to associate it to a user so I can authorize the request. But the point is that we need to do that for every single request. So gone are the days where you log into a system and then you're just statically accessing some private information or authenticated information. We need something a bit more sophisticated. And we use tokens to do this. They are great because they help us create authenticated sessions. And a session is a window of authenticated activity associated to an authenticated user. In fact, often tokens actually bear the authorization level of information. So the token itself will communicate that it's an authenticated request, and what level of authorization should be allowed can be communicated in the token itself. Usually when you create a session, the server, so creating a session often, but not always, looks like a login. So you do the authentication process, you hash the thing or whatever. And then the server sends back a token to the client. And for the duration of that session, the token will authenticate and maybe even authorize the user. So what is it like? It is like a 24-hour ticket at Disneyland. So while you've got the ticket, that is your token to access the park, the rides. You're an authenticated user within that land. Once the session is complete, nothing changes to the ticket. You still have it, but it's no longer valid. Have you ever gone to a website that you were logged in on. Let me think how to word it. So let's say, just say Facebook. You're on Facebook. Well, no one uses Facebook anymore, do they? What do you guys use? I don't know. Discord maxing or whatever. Sorry? Yeah, Moodle. Okay, you're on Moodle. Great. Thank you. Yeah, you're Moodle. How exciting. And then let's say you've got an authenticated window in Moodle and you go to sleep for the night, you come back a day or two later, and you click on a button, and then all of a sudden, it logs you out. So why did that happen? Because the token session ended while you were away. That's what happened there. So tokens aren't just a way of communicating authentication authorization, but it includes temporal authentication. Because a password is non-temporal. If you think about an authentication process, it's always going to authenticate you. But tokens don't work that way. Why is that important? Well, what if on another device, you changed your password, but on the original laptop, you just stayed authenticated? Is that a problem? Or did I not explain that clearly? Okay, I got my laptop here, and I'm on Moodle. And on my phone, I log into Moodle, and I realize, shit, I've been hacked. I changed my password. But Moodle on my desktop, my laptop is still logged in. And so the person that hacked me potentially could still do stuff. So sessions time limit our authentication. And when you change a password, you typically, in a good system, will deauthorize any previously issued tokens that may be valid. So it gives us really great control over sessions of authentication. Okay, probably getting ahead of myself. So, like I just said, a token often contains identity, which is authentication, and session claims. So for example, authorization information, like what's the role? And this is just a JavaScript object, right? That is a token. A token could just be an object. Well, this is really bad. So if you're a student on Moodle and you can interrupt a network request, get the token, and modify student to say lecturer, you could change everyone's grades. So we don't even want trusted, authenticated users to be able to change their authorization. So it's pretty clear, right? This can't be something that's like plain text. Agreed? Okay, so how do I communicate from a server, which could be, over the internet, to a client and back, that a user's authenticated and authorized for a particular level in a token that can't be modified by even the user that I trust? That's the challenge we're solving with this approach. So this would be a privilege escalation attack. I've seen privilege escalation attacks where you don't even have to modify a token. You just, for example, you log into a system and you just go /admin in the browser. There's no button because the website didn't show it. And that endpoint didn't check the authorization and just let the user in. So there's lots of ways of doing that. But if you write good code, it's so easy now to protect your endpoints correctly. That doesn't happen much. But we need to make sure that these tokens can't be intercepted and modified. So we need to detect if our authentication tokens are tampered. And tampering might be from the client, the user, or from someone in the middle, right? We don't know. Okay, so we have this concept of tamper-proof tokens, or hash-based message authentication code. Very cool because we're using this idea of hashing that we've previously discussed. Okay. So we're creating a token signed with a secret key that the server can verify hasn't been modified. A hash-based message action code. It's part of the crypto library as well. Often, so I said you kind of don't want to write authentication code. Often you will have to write some token code because it's much closer to the system. You can think of it, authentication is like I'm hiring really great, vault doors at the front of my building. throughout the whole building, right, you need to probably write some more of this type of library code. So let's just take into account that our tokens are going to be something like the user's ID and the user's access level. In the case it was a role is student. What can we do to that token such that it's provided by the server to the client continue using it for the duration of the session, but the client can't tamper with it. In fact, the client might not even be able to read it. So you sign the payload. The payload could be any object. So you can these tokens can look whatever you like. You might have some custom authorization levels, right? Every system will have different authorization levels. But the input is not a string anymore. It's just a JavaScript object. We don't know what it looks like. We turn that object into a string. That's this line here. I think basically all hashing algorithms work on strings. And we use the cryptography library in Node to create a hash-based message authentication code. With a hashing algorithm, we're using the same SHA-256, and a secret. And the secret is very important here because it allows, or maybe I'm getting ahead of myself, but this is what will allow the server to, in the future, verify that the hash wasn't manipulated. So I suppose the reason that this is important is that it's possible that a client sends back a different hashed token that, while it's a completely different hash, could resolve to the same user ID but with a different escalation level. So the server actually just needs to check that. Data is what goes into the hashing function, and we use the hexadecimal format for the output. So essentially, what do we get back from this? A string of the hexadecimal representation of the hash. Yeah. And then we just print that out. So with this approach, the server can verify mathematically that the payload hasn't been modified. This allows the client to continue to authorize themselves in the system once they've been authenticated for a session window. Okay, on the server, so you need to imagine that these are coming in, for example, in the HTTP requests. In the header of the request will be this HMAC token. Question? Okay, good question. The question was, what is a payload? It's a kind of generic term that sometimes, actually, your memories won't be this good, but I sometimes use it in 1511 when I'm describing a linked list. So if you think about a linked list from 1511, can you try? What have you got? You've got two components of the structs, right? You have the what?
The value.
The value and the next pointer. The value is the payload. So it's like the generic term for the thing that gets stored in something that stores generic things is sometimes called the payload. The other way to think of it is like, we're doing all this mathematic cryptographic techniques to this content, this object, that you need to undo, and it's like quite a heavy process. And eventually, what do you get? The payload. I don't know why we use the name, actually. I need my fact checker. Who wants to fact check? What's the etymological history of why we use the word payload in these concepts? But when I use the term, at least, it just means like, at the end of the day, if you take away all the stuff from the data structure, you get to where you really want to go. It's what you're left with. In this case, the payload is the token. Does that make sense?
It comes from military industry.
Yeah, okay, I don't know why. Military. Cool. But it does the, do you know what it means now? Yeah. So it's just like, because you could be creating tokens to communicate almost anything. So it's just the generic, it might not actually be an authentication token, it might be something else. So it's just the thing that you get after you decrypt it. Okay, so the server might issue these tokens. The client sends them back in the header of the HTTP requests to authorize themselves. So then when the server receives that, it needs to compute the signature and check that it's not been tampered with and that it's valid. And so with the library that we're using in JavaScript, like to do this from foundational principles, this is sort of roughly what you do, and I can kind of talk through it line by line. But obviously you get the token in a form of a string. Why would it typically be a string? A, because it came in via HTTP, and everything in HTTP is a string. And also, when the server created the HMAC, it creates a hexadecimal string. So we're going to get back a string. So we take that input string. We're returning either an object or nothing, right? We know our type theory a little bit better now. Why might we return an object if we can generate the what? The payload, very good. Or why might we return nothing? Well, we can't validate the hash. Exactly. Okay. Let's look at this. We create an array of encoded data and a signature, and it's assigned the result of calling split on a dot on the token. Now, tokens often have this format where we have a period in the string. And I got to remember why, but it's like you've got the payload, I think, and the signature. I think that's how it's composed. Hopefully there's a slide on it. Oh, yeah, it did too. Thank you so much. So the first component is the payload, period. The second component is the signature. And so you take, so this is basically, you can imagine a hash dot a hash. We don't know what the characters will be. That's the input. We split on the period. Tokens always have this format, so it's consistent. You'll never have a period in a hash, ever. Well, at least in the SHA families.
Doesn't that return, if it had like data as a string, what's the point of hashing it? It's just then put at the front. I don't understand that.
It's a hash of the data.
Oh, okay.
It's hashes upon hashes upon hashes.
When is data reassigned in that?
What, here?
No, in the one before. So it's like const data stringify, and then...
Data is assigned. It's here. It's because you're updating data.
Okay, that. Okay, cool.
It's an in-place function. Yeah. I bet they did that because people would otherwise forget to reassign it back to data. That would be my guess. Because if you think about, like, remember we did like the hashing functions and things? They're not in place typically in JavaScript, like you have to reassign it. But the risk of someone not reassigning the hash back to the data is so, like the cost would be so high that that's my bet, is that the only way to do it is an in-place transformation. Okay. So you get your token, it's got the payload, which is a hash, period, the signature. They're both hashes, right? There's nothing from the hash that can tell you the data or the signature, really. All right, so does this line make sense? Who says yes? Who says no? Who's not answering? That's like all of you. Oh, God. All right. We take the encoded data. It's a base64 format. We turn it to a real JavaScript data type string. And then we use that crypto library, to use the secret, update the data back, and we get the expected signature from this. So essentially what you're doing is you're doing the process again, and then you check that the expected signature, it should be the same as the signature that came on the second component of the token. And if they're not the same, then something happened to the token. It doesn't necessarily mean it was maliciously tampered. What else could have happened to it? Just something went wrong in transmission. Literally, like lightning can hit a telephone cable and manipulate the bits in a message. This stuff actually happens. But it's so resilient that it sort of survives. And then if that's the case, that they do match, you can pass the data back out of it. So if the user tried to change it, it won't work. If it gets manipulated, it won't work, and you have to re-authenticate and generate a new token. So tokens are the backbones of modern web-based authentication systems, where you have a semi-trusted client and untrusted in the middle, and you've got your server that you do trust. The server generates these signed tokens, sends them to the clients can do things, make authenticated HTTP requests with that token. The token typically is a piece of string that goes in the header of the network request. And if you do it all right, life's pretty good. Question?
For the token, why don't we instead just store the details in the token on the server and then return a randomized hash to the client so they can't actually modify the token?
Can you repeat that, please?
So right now we're sending the details in the token to the client, then signing it. Why don't we instead store the details of the token on the server?
But the secret is stored on the server.
To prevent for example, the level of access.
Mm-hmm.
Because in here, the level of access is stored in the token and is sent to the client.
Access is stored in the token and sent to the client. Yeah, that's correct.
Why don't we just not send the level of access in the token?
Okay, so I think what you're saying is, when we store when we use this, could we just not use the ID of the user, check it in the server somewhere to get the role? Is that what you're saying? And do it, you don't need to transmit it. Is that what you're sort of suggesting? Okay, great question, actually. It's a design question that you're asking. So could you build a system that works that way? Absolutely. Okay, let me give you an example of where I think it may not hold. Do you use LinkedIn? Anyone use LinkedIn? What else? What other system does this? Well, you'll probably get my idea anyway. So on LinkedIn, if you go to your page, I'm authenticated. I've got my user ID, of course, somewhere in the JSON. And I can view my page as someone who's logged out. So sometimes the role sometimes does change for an authenticated user. Facebook used to do this. Or does it still do it? You know, in Facebook you can view your profile as not a friend. Do you know what I'm talking about? Or MySpace used to do it, but I guess no one here had MySpace. MySpace was so great. You used to be able to write HTML code on MySpace and edit your page and play music and stuff. It was super good. Anyway, so sometimes you actually have legitimate reasons to modify your authorization level for the same user. And again, you could do that, but you would need something that tells the server which type of that you are doing that. And in a sense, you're just rebuilding a role level system anyway. So it's not a great answer because you're not wrong. You could not do this.
How often and when are we verifying these tokens? Every time a request is made, or every time it's passed?
It's every single time a request is made.
So ideally that would probably be its own function.
Absolutely. You will not, okay, great question. You do not want to be seeing code like this. Imagine every single endpoint had this code in it. No, what would you do? You could create a helper function. That's probably enough. Even better is you use what did we call them? Higher order function. So in Python, again, sorry to go back to Python, but in Python you have an @authorized function decorator that you can attach to your endpoints, which basically verifies the presence of these tokens and that they validate every time any endpoint with the associated authorization decorator is called. Am I making sense? But yeah, absolutely. Well, it's not any endpoint, it's any authorized endpoint. Every app will have an unauthorized endpoint. So for example, every single system that has an authentication process will have an unauthorized endpoint. What's it called? Login. Login can't be authorized because you haven't had a chance to authorize. But everything else typically, well, on a system like this will be.
So these are like our sessions, the tokens, so to speak.
Yeah, although there's no temporal data in these tokens, which is what's missing for a session. So a session will always have a time to live. And that might be, typically what you do is you store those tokens, I guess the full token, in a database table with when the token was generated. And so you can calculate when it will expire. But we just haven't described that process, but that itself basically, that is a session. The act of a session is having a time-based token that you verify and check the signature of every time an authenticated or authorized endpoint is called. And if it's elapsed, then all the signature is invalid, then the session is invalid. But often, like when a session is invalidated, you just create a new session. It's not like you have, it totally depends on the application and the level of security. So like, for example, in Moodle, if I'm signed in as like a lecturer or I have like a higher permission, they might have a tighter session window than a student. Because like the worst thing that happens if someone breaks into your account is what? They like submit an assignment you didn't do. You know what I mean? They probably could do worse, but you know what I'm saying. It's not going to like end you on SW, right? So. Oh, okay, that's basically the lecture. Let's just summarize really quickly. So now if you hear someone use the word authenticate or authorize incorrectly, you can do something to them. Authentication verifies identity. Authorization controls what level of access they have to a system. Never, ever, ever store plain text passwords. In fact, here's just a general rule, like don't store anything in plain text. There's no need. You can kind of like, well, some things you need to, but anything that's personal, anything that's private, sensitive information, try and avoid storing it. If you must store it, encrypt it at rest. So there's, even within these ideas of encryption, there's various levels. So if your server is powered down, is it still encrypted? Right, this is what at rest means. So there's, or is it encrypted in transit to the server? All these things you should be thinking about. Hashing is one way, it can't be reversed. Encryption is two-way, but you need a key. They get quite complicated. These, what we just described today, are simple techniques for these things. Tokens are great. You'll see them all over software. JWTs, if you've ever seen that, it's a JSON web token, but it's a structured format for these types of tokens. And it's great because it means that it's a consistent way to unpack the token, know what the decimal is separating on the payload and the signature and etc. They let us track our sessions once a user has authenticated for a period of time that is associated with the session. Sometimes that session duration is set by the user. So in some systems, the user can configure in like authentication settings, how long in between using this system will I need to sign in? So you might say a week, and then every week you have to, so all the tokens will expire on the database for a week or something. And HMACs make tokens tamper-proof in transit between the client and the server. And often all of this can be done with a really great, especially like one of the reasons Node and Python are so widely used is they have great authentication and authorization libraries that manage all of this for you, even to the degree in which they will give you a database that can store the tokens and the session durations and give you function decorators that you assign to authentication endpoints and check the presence of them and sign them and all of that. Thank you. And you can use all of this in your, well, you will need to use all of these concepts in your iterations from now on. Sorry? Not the tokens? Do you not use it in iteration 2 or 3? No, maybe not. I think you okay, well, sure, sorry. But you'll use the hashing and stuff, yeah.
Well, not me. That's
Oh, not you in particular. Oh my God, okay. How you divide the work up in your group is up to you. All right, any quick questions? Otherwise, I'll see you on Thursday. And then it's a long weekend. How exciting. Thanks, everyone.